Hello everyone, today we're going to look at the standard normal distribution. The standard normal distribution is a bell-shaped curve and it comes up in a lot of places, and we'll see examples of this throughout the course. We say that x is normally distributed with mean mu and standard deviation sigma. So we have this way that we write something as normally distributed. If I wanted to look at the equation for the distribution, it's f of x equals 1 over sigma times the square root of 2 pi e to the power of negative 1/2 times x minus mu over sigma squared. This is a very complicated formula, and in order to find probabilities, we would have to integrate this, and it's not even integrable. So we're not going to work with the equation at all, so you don't have to worry about it. We're going to use either a table or Excel to find the values that we need. For right now, we're going to focus on the standard normal distribution, which is when mu is 0 and sigma is 1. Typically, we'll use the variable z when we're talking about the standard normal curve. So we have that z is normally distributed with mean 0 and standard deviation 1. And here's a picture of what that looks like. So again, it's a bell curve. The picture looks like a bell. And then the middle is the 0. So that is the mean, it is the median, it is also the mode. So that's the nice thing about normally distributed variables. Mu is also the median and the mode. If we have a normal curve that isn't standard, we can standardize it with the equation z equals x minus mu over sigma. And we've actually seen this before a few sections back. This is going to help us compare values from different distributions, and it will also allow us to use the standard normal table, which we'll talk about in the next lesson. So as our first example, what is the z-score of x equals 7 if x is normally distributed with mean 5 and standard deviation 2.5? So I'm going to plug it into my equation above. So x is 7, mu is 5, and sigma is 2.5. So I have 7 minus 5 over 2.5. which gives me a value of 0.8. What is the z-score of x equals negative 2 if x is normally distributed with mean of 0.5 and a standard deviation of 0.5? So I'll plug in my x, my mu, and my sigma, and I have negative 2 minus 0.5 divided by 0.5, and that gives me negative 5. Notice that when z is positive, that means that my x value was above the mean, and if z is negative, that means my x value was below the mean. Remember, back when we first started talking about standard deviations, this z, or the z-score, is how many standard deviations away from the mean our value x is. So in the first case, 7 is 0.8 standard deviations, or 0.8 of 2.5, away from the mean, which was 5. Negative 2 is negative 5 standard deviations away, so it's negative 5.5s away from the mean. We're also going to talk a little bit about what's called the empirical rule. We use this a lot to make sure that our answers make sense. It's going to be a generalization of a normal curve. So if x is normally distributed with mean mu and standard deviation sigma, then the empirical rule says the following 3 things. It says about 68% of the x values lie within one standard deviation, which means between x minus sigma and x plus sigma. It says that 95% of the x values lie within 2 standard deviations, which is x minus 2 sigma and x plus 2 sigma. And then lastly, it says that about 99.7%, which is almost all of them, lie within 3 standard deviations, so between x minus 3 sigma and x plus 3 sigma. So for instance, if the mean height of a certain group of men is 70 inches, with sigma being 2 inches, what does the empirical rule tell us? Well, it tells us that 68% of the values lie between 68 inches and 72 inches. So this is exactly x, which is 70, minus sigma, which is 2, so 68, and then 70 plus 2, which is 72 inches. It also tells us that 95% of the values lie between 66 and 74 inches, which is 70 minus 4 and 70 plus 4. And then the last one tells us that 99.7% of the x values, and remember the x values are heights of men, so 99.7% of men have a height between 64 inches and 76 inches. So 70 minus 6 and 70 plus 6. Okay, so that's what the empirical rule is telling us. And again, generally we'll just use it to say, does our answer make sense? And then as our last couple examples, we're going to suppose that x is normally distributed with a mean of 20 and a standard deviation of 4. Find the following. A, the z-score associated with an x value of 15. So I meant to hide the answer, but that's all right. So if I want to find the z-score, I'm going to be using that equation that we had before. So z equals x 15 minus mu 20 over sigma 4. And if I do that, I get negative 1.25. So again, the fact that it's negative is telling me that my x value is below the mean, and 15 is below 20. And then the 1.25 is how many standard deviations, or how many 4s, away from 20 15 is. And if you remember that rule of thumb, the usual values are within plus or minus 2 sigma. We see that 15 is not an unusual value because it's only within 1.25 standard deviations of the mean. What if I want to go backwards? What if I want to find the x value associated with a z-score of 2? So what is that area that just becomes unusually large? Okay, so if you're within 2 standard deviations, you're considered a usual value. Remember, going back to the empirical rule, that was 95%. So 95% of values are within 2 standard deviations. So we want to know what is that value that's associated with a standard deviation, with a z-score of 2. So if I have that z equals x minus mu over sigma, I can solve that equation for z, and I get solve that equation for x, and x equals sigma z plus mu. So I'd multiply both sides by sigma and then add the mu over. When I plug in my values, I get the following: 28. So 28 is where the usual and then unusual values, that's the separating point. Anything above 28 would be considered unusually large. Okay. So read through the book. Let me know if you have any questions. Good luck.